Hello and welcome to this video. We're going to be actually having two videos, one for goodness of fit and the other one is chi-square for independency. And first of all, let's go ahead and know what is a chi-square. A chi-square is a statistical test that will be used with categorical values. Categorical values such as like fair, not fair. Also, it will be used with two variable such as political affiliation for male and female. And so if we do actually have a test that is going to be closely related to observe the distribution and how it matches those expected values, this is referred to as a goodness of fit. But let me go ahead and explain what do we mean by that. If you take a coin, when I flip the coin, I get two expected values, either head and head or rather tail, and the probability of getting a head or a tail is 50%. So this is the expected value. If I throw, let's say 300 times, and I got in this case 300 times the coin, and I got 157 heads, and of course what is going to happen here, 143 for the tail. So this are the observed values, but the expected value, because the chances 50% for the tail is going to be half of those for the tail and half of those for the heads, which means 300 is going to be divided between two. So this is very clear with the tail. Let's get a little bit more involved if we are going to throw a die. A die has 6 faces, with the values 1, 2, 3, 4, 5, 6. Let's go ahead and make it a story here. It's easy to follow when it's a story. If we have a casino and this person who's running the die claim that his die is fair, it's going to be either fair or unfair. If this die is a cheat or it's really an honest die. So we observed the throws of the die. We found out that we got 10 when with value number 1 or face number 1. We got 90 with face 2. We got 1 with face 3. We got 99 with 4, and 5 with 5, and 95 with 6. The total of the observed values are 300 if I added all of those using the sum function here in Excel. Immediately I suspected with my friend who watching this that this is something wrong about this, because this die is kind of weird, knowing that I'm going to get 143 and 999 for 4, but I cannot tell the person directly that this die is a cheat, and I wanted to be able to prove that scientifically. So he is guilty, but I mean he's not guilty until proven his guilt, or he might be innocent. So let's go ahead and first of all calculate the expected value. The expected values are going to be the 50 for each one, because the 300, that's the number of the total divided by 6, which is the 6 possible values for a die, for the die 6 faces, is 50 for each one of them. So if you do notice here, 50 is for each one of them, and total is still 300 for the expected value, just like it is for the observed value. So if you go back to the first test, as now it should make a little bit more sense, there is a need to estimate how closely an observed value, those are the observed values, versus the expected distribution, that's the fair side of the throwing a die. Each one of these values should be 50 out of the 300, because the probability of each one of them is 1 over 6. 1 over 6. So this is basically what is going to be for the expected values. And notice the expected values are going to be equal in this case for each face of the die. So this is basically the first type of chi-square. Later we're going to in another video, we're going to talk about the random variable, whether they are independent of each other or not. So let's wait for that videos to discuss the second item in my definition of a chi-square. So let's focus now again on this categorical testing, whether the die that this person is using in the casino, whether it's a fair or not. So let's go ahead and start with the null, stating the hypothesis. And first of all, this is my item number 1. Let me go ahead and insert insert. It's better to insert a text box here, and I'll be able to use it as my editor here. It's much easier than using cells. So I'm going to go ahead and say number one, and it's going to be, as you notice here, it's going to be hypothesis. The null hypothesis, it's going to be the die is fair. So there is innocent to start with. The alternative hypothesis, is going to be the die is a cheat or not fair. So this is here, die is not fair. Okay. And now this is my null hypothesis versus my alternative hypothesis. I need to prove somehow that when my intuition now, this die is really something wrong with it, but I will go ahead and have to do the complete testing, my hypothesis testing, to prove this or not. So this is the first and second. Since nothing giving us about our confidence interval or level, we're going to assume alpha is going to be equal to 0.05. So we're going to assume at 95%. So this is alpha at 0.05, nothing giving it to us about alpha, so we'll be happy with 0.05. And we're going to move on to discover where is the critical or the rejection region starts, the rejection region. And that is going to be looked at the tables, or better yet, we're going to be looking in Minitab in order to find the value for the start value of the rejection region. So I'm going to go to Minitab, and I'm going to graph, and I'm going to probability distribution, and I'm going to go to the view probability, and here we go. And now I need to change the normal, which is the default one, to chi-square, here chi-square, and we're going to chi-square, and we're going to talk about now something called the degree of freedom in a second, and we need to explain this. The degree of the freedom is determined by the number of the rows minus 1 multiplied by the number of the columns minus 1. However you look at it, I have either 6 rows by 2 columns or 6 columns by 2 rows. So 6 minus 1, if we talked about 6 rows, okay, then it's going to be 6 minus 1 is 5. And we talk about 2 columns, then it's going to be 2 minus 1, which is 1. So 5 multiplied by 1, the degree of the freedom is 5. So again, the degree of the freedoms is calculated as the number of the rows minus 1 multiplied by the number of columns minus 1. So if you notice here, let me go ahead and say it here before I run this. If I say number 1, 2, 3, 4, 5, and 6, then I have the observed values. I'm going to get those from Excel. The observed values are going to be, let me go ahead and refresh my memory here, 1090, 199, 595. Okay, so it's going to be 1090, 199, 5, and 95. So those are the observed values. So I have here, if I wrote them this way, it's going to be 6 rows with 2 columns. 6 rows with 2 columns. So the graph here, again, back to the probability distribution, view the probability. I wanted to go ahead and get the chi-square. Here we go, chi-square. And if I say here 6 minus 1 multiplied by 2 minus 1 is going to give me 5. 5 multiplied by 1 is 5. And I'm going to hit OK. And here we go. We ended up, as you notice here, we ended up with the critical region start at 11.07. So for me to reject the null hypothesis and prove to this guy that his die is not fair, I have to get a value, a calculated value bigger than starting at 11.07. Of course, the bigger it is than 11.07, it's going to be the more determined the conclusion that I actually got to it, the more I prove to this individual that my initial intuition is correct and his die is some sort of is a cheat. So let's go ahead and copy that into my calculation here in Excel. It's going to be 11.05. Now, 07, sorry. We're going to move now in order to calculate the chi-square, okay, calculate the chi-square based on the given values. And how are we going to do this? There is an actual formula. I took it from this website, easy website that it's going to, here we go, this website. It's called Math is Fun, and I need to give a credit for the mathisfun.com. So let's go back to this one here, and I see that the chi-square, which it looks like x squared, but it's chi-square. It's the sigma, which means the summation or the sum of all the observed value minus the expected value raised to the second power divided by the expected value. So let's go to Excel and do this. Let's go to Excel, and I'm going to go to my sheet 1. So these are my basically, I could go ahead and calculate this. If I wanted to go ahead and say expected observed value, which is this my observed value, minus my expected value raised to the second power divided by my expected value. That's for the first item. So I could do 6 of them, of course. Drag it down. Here we go. Drag it down. And then I'll add sum. The sigma is the sum all of them. And as you notice here, I'm summing all of those. And I got, wow, 241.04. If I told you earlier, I'm happy with anything that is larger than equal 11.07 in order for me to reject the null hypothesis. I get 241. That's way too inside the rejection region. So in this case, we're going to actually say we reject the null hypothesis very strongly. So the conclusion here is going to, or let's go back to Excel and say the calculated is going to be 241.04, and it's much bigger than the 11.0. So now 5, we reject the null hypothesis. The die is fair, and the null hypothesis, okay, and therefore the die is not fair, which goes with our initial intuition. The die is not fair. So now we're going to use now the p-value in order to determine the b-value. If b-value is less than 0.05, we're going to reject the null hypothesis. If the v-value is greater than 0.05, which is the alpha value, then if it's a greater, we will fail to reject the null hypothesis. In this case, we wanted to make sure that the b-value is less than 0.05, or that's going to contradict everything we have done. So let's go to Minitab, and I'm going to go ahead and close it, and I'm going now to run the statistical analysis for the chi-square. I'm not going to the basic statistics as I've done with the one sample for the z-test and sample for t and one sample for the proportion. I'm going to go to tables, and I'm going to go to the chi-square goodness of fit. And that's going to tell me, since I put the data right here, the observed count, which is, I'm going to click right in here. Okay, here we go. Those should have been, I'm going to cut this and put them right here, starting with this area there, starting with this. Okay, maybe I lost those. Paste those here. Okay, let me go ahead and do it one more time. Number die here, and it's going to be 1, 2. I could use similar to the fill handle in Excel, and all the way to 6. Then we have here, if I recall clearly, 10, 90, 1, 99, 5, and 95. So it has to be that label. label has to be on the gray area here. So let's go ahead and get the stat. I'm glad I made this mistake, so in case somebody also did it. And we're going to go ahead and get to, not this one, sorry. We're going to go to stat. We're going to go to the table. I'm going to go to the chi-square goodness of fit. And now, if I click on here, notice that I have the data coming from the spreadsheet or spreadsheet lookalike. Here, we're going to go to the die, click on it. The categorical data, categorical name is optional, which is the 1, 2, 3. I'm still going to put it. And now we're going to go to the graph. I only choose the bar graph for the observed versus the expected values. Say OK and run this goodness of fit. And here we go. Let me remove the graph in order to see the nice calculation here. Notice the chi-square, we did calculate it manually, which we should be able to do that on the test. And look at the p-value, which is almost 0. It's actually showing at 0, but it's, if you go to the left, maybe it's not 0, but it's so small, even they rounded it to 0, 0.000. And we're going to conclude in this case, since p-value is way too small, 0.000, which is less than 0.05. There we go, 0.05. Then we fail to reject the null hypothesis. Then we reject the null hypothesis. We reject the null hypothesis, and we reject the null hypothesis in that the die is unfair. Therefore, let me go ahead and slow down. Therefore, the die is not fair. Okay, that should do the whole test. And thank you for watching. I hope to see you in the next video. Thanks.